Alright, grade 11 chemistry, unit 4. Let's get started on this one. This is going to be a shorter unit than we've had before. It's only 4 videos long. That's because we've set up a lot of the background already with our stoichiometry unit and some of the other stuff, like when we talked about double displacement reactions and solubility. So you've already seen like solubility tables and moles and stuff like that. So we can go a bit faster. This one's called Solutions and Solubility. It's all about, well, solutions. Classic chemistry, stock photo, blue things, yellow things, whatever. Here's what the unit's about. Solutions of various types. We'll talk about why things dissolve in water, some solubility rules. Talk about water quality, so that's going to be a project. The project's actually going to involve the fish tank over there. I'm going to do some tests on the fish tank, and you're going to have to tell me like what parameters are out of line, stuff like that. We're going to go deeper into acids and bases, so I'll talk more about acids and bases. We'll talk about quantities in solutions, so we're going to take that mole concept and apply it to solutions. We're going to do a little bit of that today, but most of that's going to be later this week. Okay, but today's lesson, we're going to first talk about what a solution is, because some of you might have forgotten. I'll talk about solubility trends in gases and solids. We're going to talk about measurements of concentration, so different ways to measure the concentration of something. And we'll get into molar concentrations, which is the way that chemists prefer to measure concentration. Alright, so let's just jump right into it. Excuse me. Solution is what we call a homogeneous mixture, which means that it looks like one substance, right? One substance. It means that there's always something that's dissolved in something else. So there has to be something that is doing the dissolving and something that is being dissolved, right? The substance that's doing the dissolving, which is the thing in the greatest amount, is the solvent, and the substance or substances present in small amounts, those are solutes. So solvent and solute. You'll often see solvent used, paint thinner or nail polish remover is a solvent because it's able to dissolve whatever is attached to something. A solution always has just one solvent but have many solutes. So for example, here's some water, just some tap water that I grabbed from my kitchen. The solvent is clearly water, but in there's some sodium and some chlorine and some fluorine because they put fluorine in the water, some aluminum, various trace amounts of all kinds of different things. We're going to talk about water quality later this week. You'll see that there's all kinds of stuff in this, in very small amounts, but all kinds of stuff are in there. So let's talk about types of solutions real quick. Just have a look at the photos here. This is just salt going into water. So that's a solid going into a liquid. And these are different types of brass and bronze and stuff like that. So these are solids dissolved in solids, right? So for example, stainless steel, chromium and manganese, that's dissolved in iron. A lot of things are solids dissolved in liquids. Liquid dissolved in liquid also happens a lot, like nail polish remover is acetone dissolved in water. Vinegar is acetic acid dissolved in water. Things like that. Vegetable oil is a bunch of different types of oil all dissolved in each other. You can also get gas dissolved in a liquid, so like oxygen for the fish. Right? Clearly my fish are alive back there. And they must be getting the oxygen from somewhere because they're animals. They're pulling it right out of the water with their gills. So there's oxygen dissolved in the water. Carbon dioxide can be dissolved in water for the soft drinks. So I'm sure we've all experienced cracking open a carbonated beverage and the CO2 comes out. And you can also have gases dissolved in gases. So air is mostly nitrogen, 78% nitrogen, 20% oxygen, about 1% argon, and a bunch of other gases. So there's all these gases in solution out here. And there's other kinds of, gas mixtures. Welders, for example, will have a mix of gases that they use for welding. Divers will put different mixes because the nitrogen will give them the bends at pressure. We've got a whole unit on gases coming up, so this is our last unit. So more on gases later. One big thing about solutions, though, solutions have to look homogeneous, have to look like one substance. And in water, typically that means that they're transparent. So when you have water like this water has a bunch of stuff all dissolved in it, but it looks transparent. Meanwhile, this one here, which is apple cider, right? It has stuff floating in it. It has like the little chunks of the pulp of the apple floating in it, and those little chunks make it opaque, and that means that it's not a solution. This is not a solution. Technically, this is a suspension. That's solutions versus suspensions. Apple juice, though, if you take apple juice instead of apple cider, that's a solution because it looks transparent. You can see through it. There's no solids floating in it. Which means milk isn't a solution. Milk is also a suspension. The white opaqueness of milk is little tiny fat bubbles floating in the milk. Okay, now we're getting into solubility. So we finished solutions. Let's talk about solutions. So let's talk about solubility and solubility trends. Yeah, so let's talk about solubility. So different things can dissolve in water to different degrees. You guys might know, for example, that you can dissolve a lot of sugar in water, a lot. And it also changes depending on temperature and other factors like that. So you can dissolve lots of sugar in water. You can't dissolve nearly as much baking soda in water, a tenth of the amount. And then gasoline basically doesn't mix with water at all, and stuff like that. Typically, this is a pretty standard definition of solubility: grams per 100 milliliters. So grams per 100 mils of water. So you start with 100 mils of water and you put in X amount of grams until it's saturated. It's a pretty standard way to explain solubility. Glucose is almost 100 grams per 100 mils. Sucrose, table sugar, is actually over 100 grams per 100 mils. You can get a lot of sugar into water. If you've ever made syrup, you'll know that. Now, insoluble, we have this thing called insoluble. Well, nothing's really insoluble. Even gasoline, a little bit of it stays in the water. Right? And we know that vegetable oil and water don't mix, but a little bit of that vegetable oil will stay with that water. But generally what we mean with insoluble is less than 0.1 grams of the substance can dissolve in 100 milliliters of water. So this is like 200 mils of water, right? This jar is probably about 200 mils. 0.2 grams is ridiculously tiny, right? So you're talking about tiny amounts, but that insoluble still leads to important concepts. Like, for example, oxygen gas is only has a solubility of 0.0008 grams per 100 mils at 25 degrees Celsius and at atmospheric pressure, and yet the fish, the light's off, but the fish can breathe just fine. They have enough oxygen in there to breathe. So even though it's insoluble, it still has an effect. Anywhere between 0.1 grams and 1 gram is sometimes called sparingly soluble or slightly soluble, so I guess baking soda would probably be sparingly soluble or slightly soluble. No, not baking soda, sorry. I don't know, something. Maybe caffeine might be somewhere in that slightly soluble zone. Yeah. Alright, so that's that. Now, what if something can mix in any proportion, right? What if grams per 100 mils doesn't work anymore? What if it's liquids and liquids? What if it's gases and gases? What if it's metals and metals? Well, if you can mix in any proportion, it's miscible. So miscible means you can mix them in any amount you want. You can have, for example, alcohol and water. In your first aid kit, you probably have some 70% alcohol in water. You can have 99% alcohol in water. You can have 10% alcohol in water. You can any proportion of alcohol in water. Liquid, gas, and solid. Certain ones can mix in any proportion you want. Gas, very easy to mix, right? They're gases. They just fly around, so the molecules don't really interact with each other. Metals typically are miscible with each other. That's how you make alloys. You can make ethanol and water, ethylene glycol, antifreeze, and water. Different amounts of ethylene glycol will make the freezing point different amounts. Here's gas, a vapor mixing with air, and you see that miscibility. And if it's 50%, you only get a solvent or a solute. And really, with miscible ones, it's hard to tell if there's really a solvent or a solute. They're just in a nice mixture. All right. And the next thing is saturation. Ooh, that's not what I wanted to do. Saturation. Saturation, we have these words: dilute means not a lot of solute, concentrated means lots of solute, and saturated means as much solute as it can possibly carry. Okay? As much solute as it can possibly carry. So if you dump a bunch of salt in water, a lot of the salt will go up into the water, but past a certain point, you're just going to keep putting extra salt, solid salt, into the bottom. So that's the difference between dilute, concentrated, and saturated. And then if you have too much solute, you can have something that's called supersaturated. And the reason for that is often crystals need something to start with when they form. And so if you have a very, very smooth container, the crystal won't start anywhere. So you can see some really cool videos of supersaturated solutions. I'll link one down below of sodium acetate, the classic supersaturated solution, the hot ice they call it. Yeah, so that's saturated, dilute. Let's talk about water and the solubility trends for water. Water is sometimes called the universal solvent. Nickname because it dissolves so many things. Right? If you guys know this, we use water to wash our clothes, and we use water to wash our pots and pans and things like that. It dissolves stuff, and hot water dissolves stuff really well. The reason for that is that water is small and it's polar, but it's not super polar, so it kind of sticks to itself, but it can open up. So it's like water likes to be in a certain arrangement, but then can also kind of get opened up and then come back to the same arrangement. So it makes kind of like cages. It surrounds things and makes cages. I'll link a video of salt dissolving in water. I think I actually showed that video in Unit 1 with the salt dissolving in the water from the Museum of Nature. But I'll link it down below again. Have a look. So it sticks to itself, and it can surround lots of different things. It can even dissolve gases, right? So it can actually, a gas molecule can come in and get trapped in the little cage of water molecules that are surrounding it, like you see. It surrounds stuff. So that's water. Water is polarity, but not too strong of a polarity. The fact that it's small and liquid, it can trap stuff and surround it. But some things don't dissolve in water. You guys know, for example, that gasoline won't dissolve in water. Vegetable oil won't dissolve in water. Many other things won't dissolve in water. Many solids won't dissolve in water. Right? This plastic won't dissolve in water, for example. Let's talk about some general solubility trends for water. First thing is ionic compounds tend to be quite soluble, especially the ones that have low charge, so like sodium, fluorine, chlorine, ammonium, those kinds of things, nitrates, they're very, very soluble. You have to check a solubility table. You guys remember, hopefully, solubility tables from Unit 2. We were using them for double displacement reactions. We do that grid and you find out if it's soluble or not. Molecular compounds depends on size and overall polarity. We talk a lot about this in grade 12. And I've already made a video on that with the grade 12s because it was in our first unit. You can have a look at that if you want some bonus content. This is alcohol, just alcohol in general. Tell me what trend you see. This is, 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon. Here's the solubility in, there's actually moles per 100 grams rather than grams per 100 mils. It's pretty good. So what do you see? Obviously, you can see that as we go up in carbon number, the more carbons we add, the less soluble it gets. And in fact, the first three, methanol, ethanol, and propanol, are all infinitely soluble, so they're miscible with water. What that tells you is that the water can surround the methanol very easily. because the methanol is small. The water also coordinates to those OH groups with hydrogen bonds, and so it's able to dissolve it easily. But as you get more and more carbons, the water has more trouble surrounding it, more trouble attaching to it, because it's just carbons and hydrogens. It's very non-polar kind of bonds. If we think back to Unit 1 with the polarity of the bonds, and so it becomes less soluble in water the longer it gets. And so we have this rule. The rule, the rule is on the next page. What about fats and oils? Fats will dissolve in oils. Lots of things can dissolve in various oils. Oil itself, like vegetable oil, is a bunch of different oils, all dissolved in each other. And what happens is they just kind of like slide in and coexist. So it's a solution. It's not like anything's surrounding anything or really attached to anything. It's just kind of existing together. The weak intermolecular forces. So they're just kind of chilling. But that means that they can surround and grab nonpolar molecules. So stuff like wax and things like that. You can dissolve all kinds of interesting things in there. So there's a rule. The golden rule here is like dissolves like. Like dissolves like. So polar substances dissolve polar substances. Nonpolar dissolves nonpolar. Small is more likely to dissolve in small because it can be surrounded. Big is more likely to dissolve in big because they can just kind of lie next to each other if they're long chains. So yeah, small and polar will dissolve small and polar. Big and nonpolar will dissolve big and nonpolar. So let's compare water and vegetable oil real quick. Water and vegetable oil, as you know, won't mix. Your science teacher in grade 6 might have said, oh, they have different densities, that's why they don't mix. Well, no, that's wrong. This is, some common ideas of vegetable oil. Look at all the carbons, right? Tons and tons of carbons, just big long carbon chains. They're long, they're not very polar. There's a bit of polarity on the end, but the rest of it's not very polar. Water, as you know, H2O, small, polar. They're on opposite ends of the thing in both size and polarity, and so they don't mix. Water has trouble surrounding the vegetable oil. Vegetable oil has trouble getting in between the water because the water likes itself so much, and so that's what happens. And here's what happens to oil and water. The oil, the polar part of the oil, this bit, will face out towards the water, and the non-polar part all kind of gets shoved in to the middle because the water likes itself so much. The water really likes itself, and so the oil gets pushed into these little rounds. And you can try it yourself with vegetable oil and water. It's pretty fun to watch the vegetable oil actually make little bubbles. Or better yet, if you pour vegetable oil into a jar or a glass like this and just drop some water into it, you'll get perfect spheres of water slowly coming down through the vegetable oil. You get like kind of water, snow, it's neat, and it'll all gather at the bottom and all get together. So the water in the vegetable oil will also do the same thing. It'll all kind of group up, it'll clique together. So that's kind of a fun one. If you have a big tall vase or something, you can fill it with vegetable oil, put some water drops in it, and watch the water drops slowly fall down as perfect circles. And then you can, the oil is on top and the water's on the bottom because they're different densities, so you just reuse the oil, most of the oil. So that's oil and water. Let's talk about solubility trends. So the first solubility rule is like dissolves like. That's our first solubility rule. If you have something small and polar like methanol, water is going to dissolve it like crazy. It'll dissolve at any temperature, at any proportion. Now the second rule is that solids tend to dissolve better with hot water. So here's the graph of that. Solubility of solids tends to increase with the temperature of the water. So you have a bunch of different solids here. Sucrose, right? At 0 degrees Celsius, 200 grams. At 40 degrees Celsius, 50 degrees Celsius, it's 250, and then it just keeps going up from there. You can dissolve a lot of sugar in water. Ammonium nitrate, even better. Glucose has this crazy curve. Calcium chloride has a cool curve. This is sodium acetate. That's the supersaturated solution I'm going to put to the bottom. And basically the other ones. One neat one here is salt, sodium chloride, which is this kind of like brown line here, is very flat. Very, 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 very flat. Very flat. And some even go down, like lithium sulfate actually goes down, and yeah, but generally the trend is upwards with temperature. The question is why? Think about that. Why would hot water be better at dissolving things? Now that I've told you that water likes to surround things and kind of make little cages and stuff like that. Well, the answer is basically the hot water, because it's moving faster, can kind of get into the nooks and crannies and kind of pull the thing apart. And it has more energy to come in and grab things and pull them away. It's also a bit more spread out. As you heat up water, it expands a little bit, so you've got more room inside the cage to pull your solid into, to get the ions apart and things like that. So yeah, typically the solubility of solids increases with temperature, with some exceptions. Like salt is very notably just flat. Very, very flat. And certain ones even go down. But most of the time it goes up. Now gases are different, right? What happens with gases is that they get kind of trapped. They get trapped in the water. And you have to think about a gas dissolving in water as kind of an equilibrium. Gas is coming in and hitting the water, right? They're all fat little small molecules moving very quickly all over the place, and if it hits the water, there's a chance that the water will trap it. Then the water will move around as water does and bring the gas further down. So that's what's happening in my aquarium. It needs to have room on the top, right? It needs to have air exchange on the top so that the air can come in. And I've even got the little pump, that little waterfall thing, right, to help push air down into get it down to the bottom of the aquarium. But at the same time, there's molecules right at the surface that are trapped in that cage, but they can break free when the cage gets too close to the surface. They'll just break free and go back into gas form. So you have this thing set up back and forth, back and forth, back and forth. If you increase the pressure of a gas, it gets more soluble. So you push the partial pressure of the gas, it makes gases more soluble. A good example of this is like soda stream machines. They put a bunch of CO2 on top of the water, and then the CO2, because there's a bunch of them up on top of the water, there's a bunch of collisions, and they go down and dissolve. They get trapped in the water. As we talked about, this also happens environmentally. The CO2 going up is increasing the amount of CO2 in our oceans and stuff like that. So more pressure makes it more soluble, less pressure makes it less soluble. You can actually take the gas out of water with a vacuum pump, which is pretty fun. Yeah. This is kind of back and forth of molecules of gas dissolving in the water and gas leaving the water. Which means, interestingly, that we have the opposite trend in gas solubility versus temperature. Right? Gas solubility versus temperature. Here's the solubility in moles per liter of different gases in water. And here's the temperature down here from 0 to 30. You can see that the solubility goes down with increasing temperatures. Solubility goes down with increasing temperatures. It goes down. So less oxygen in the water, less methane and less carbon dioxide, less stuff in the water. So the hotter it gets, the less soluble a gas is. Why would that happen? Why is it the opposite from the solid solubility? In solid solubility, though, they were moving faster, they were able to pull things apart better. In gases, remember that they're trapped in a cage, and if they weren't in that cage, they would be free, they would fly away. So the faster vibration of the water molecules means the cage is looser, and so the gas molecule has more chance to fly out. And so you end up with the gas flying out very quickly. You can test this yourself if you want. You just have to pour 2 glasses of something carbonated, like, I don't know, some Coke or ginger ale or whatever. Pour 2 glasses of something carbonated, stick one in the microwave for a little bit, and keep the other one at room temperature, or better yet, stick one in the fridge and keep the other one at room temperature. The one in the fridge will go flat way slower than the one at room temperature. You can try that out if you want. Yeah. So, yeah, that's the trend for gases. And here's the general rule. All right, so solids increases with temperature with some exceptions. That's what it says behind my face, some exceptions. Solubility of gases will decrease with temperature. So there's this opposite. Solubility of solids increases with temperature. Solubility of gases decreases with temperature. And solubility of gases will increase with partial pressure. Partial pressure is the pressure of that gas. So if you increase the pressure of a different gas, that first gas won't change in solubility. If you increase the pressure of that specific gas, you will change the solubility. This is actually very important for like medicine when you talk about ventilators and getting oxygen into people's blood. They have to increase the partial pressure of oxygen, and they can do it with just increasing the oxygen supply rather than the pressure in the whole room. So you'll see people with like the things in their noses that are just giving them pure oxygen. It's not increasing the pressure of the room air. It's increasing just the pressure of the oxygen, and that's enough. It will get into their blood. Okay, that's solubility rules. Let's get into our last piece, which is measurements of concentration and then molar concentration. So I'm going to fly through these pretty quick. Yeah, so we're going to talk about concentrations and expressing concentrations. Concentration is the amount of solute in the solvent. High concentration is concentrated, low concentration is dilute. And the important thing about concentration is that it doesn't change with volume. So like this apple cider is a certain concentration. There's a certain amount of like apple stuff in my water. If I drink some, right, I've got less of it now. There's less volume, but it's the same concentration because it's the same color kind of thing, right? It's per volume is the big thing, right? So we always express it per volume, right? If I then take some water and I pour it into there, that is now less concentrated. Even though there's, the same volume now, back to the original volume, now it's less concentrated. There's less apple stuff per liter, so it's less concentrated. I have diluted it. It is now more dilute. So more diluted, more concentrated. So we always express this as a ratio of solute versus solvent. I would have had, some amount of, grams of apple per liter, and now I've just cut that in half. I have less grams of apple per liter. So concentration is independent of amount. Another example, a small coffee and a large coffee have the same concentration of caffeine in the coffee. Now an espresso shot has way more caffeine concentration in that little tiny espresso shot, but it might have the same relative amount of caffeine as a big coffee or whatever. So that's concentration. That's expressing concentration. And we always express concentration in terms of mass or volume of the final solution, of how much of the total thing we have. This is different from solubility, where we start with 100 mils of water and put in more and more and more stuff until it doesn't dissolve anymore, which means the final volume would be higher than 100 mils. In this case, it's always per 100 mils of this solution, right, of the whole thing. And if I decrease the concentration by adding some water, now I've got a lower concentration, but it's per volume of the final solution, even though I've added some more water. Yeah. So that's, so we express all of this in the volume of the final solution. So there's three common percentages of concentration, because people understand percentages. Right. For example, I've got some stuff here from my, from my house. Here's some vinegar. It's some vinegar, and if I zoom in on it, somewhere in here, there we go. 7%. 7% acetic acid by volume. Now, typical vinegar is 5%, so you know that this stuff is stronger than normal vinegar. People understand percentages. And I've got this. It's an iodine tincture. It's a topical antiseptic, so like, you know, cleans wounds and stuff. And it says, hopefully, you see it, there it is, 5%, 2.5%. So you can understand it's 2.5%. Right? Or this one, this is a steroid cream, 1.5%. You know, there's various other ones. Maybe the most common one people see is your 70% rubbing alcohol. You buy 70%, you can also buy 99%, so you know that there's more alcohol per volume. So it's a percent per volume or per mass or per whatever. So commonly you've got three types: mass per volume, mass per mass, and volume per volume. We're going to go through each one and talk about common uses of these in household ones. You saw that all of these have percents. So percent is probably the easiest to mass by volume, probably the easiest to understand. You know, it's how much mass versus mass of solute versus the volume of the solution. So 1% would be 1 gram of whatever it is per 100 mils. And you see that in, you know, a lot of medicine. So this thing, for example, this Paradex, which is a mouthwash, is 0.12%. That's going to be mass of the active ingredient per volume of solution. So you'll see that reported a lot in medicine. So medicine, very commonly used as a mass per volume. Because, you know, you take a liquid, you can measure how much of this stuff to give. This one says 15 mils, like a capful, and then you know, that's how much you take, and it's a specific dosage that you can get. So saline, for example, 0.9% sodium chloride, mass per volume. So it's a mass per volume, so 0.9%. Right, and even says in here, if you look close enough, it says each 100 mils contains 900 milligrams of sodium chloride. So it even says, you know, it's a stock photo, but yeah, each 100 mils contains 900 milligrams sodium chloride, mass per volume. Then there's mass per mass. It's usually used for solid-solid, but it can be used for other things. So for example, this one here, this 1.5% is actually weight by weight. So this thing, you can actually see it, weight per weight. Weight over weight, 1.5%. Because this is a cream, and you don't really measure the volume of a cream so much, right? So it's more important to talk about the weight. Mass per mass is usually grams per grams, kilograms per kilograms, whatever. This one, I don't know, probably milligrams or something like that. It's very commonly used in metals. So for example, sterling silver, 92.5% silver and 7.5% copper. It's not pure silver. 24 karat gold is the pure gold, it's 100%, but usually you get like 18 karat or 14 karat or 10 karat because it's too soft, so it's alloyed. Usually it's copper, it's in the gold. You get red gold and, you know, white gold and whatever. Stainless steel is usually 18% chromium, 8% nickel, 73% iron, and then some other stuff. So yeah, you got lots of examples of solid solutions in the real world of weight by weight. Weight by weight. And then there's volume by volume. So this one, the vinegar here is 7%, and it says, here in English, by volume. 7% acetic acid by volume. So it's a volume per volume. It's the same thing with the rubbing alcohol, the 70%. It's going to be, and it's on here, there you see it right there, 70% V over V, volume over volume. Yeah, so it's used for liquid measures, volume of solute over volume of solution. So it's 1 milliliter per 100 mils, or 1 liter per 100 liters, or whatever. Used for alcohol, gasoline, hydrogen peroxide. You'll see it used for alcoholic beverages like ethanol beverages, right? Like beer is like 5% and wine is like 10%, and various liquors are like 20 and 30 and 40%. Well, that's a volume by volume. So yeah, those are pretty easy to understand. They're made to be easy to understand by people. That's why they're used in household goods like these things, right? We can understand 70% is weaker than 90% for that kind of stuff. But chemists, we haven't talked about chemists yet. One last thing is very tiny concentrations, very tiny concentrations. We use stuff like parts per million and parts per billion. That's ppm and ppb. We'll talk more about these when we talk about water contamination, because usually things are in ppm or ppb amounts. There's these typical shortcuts where a ppm is a milligram per liter, 1 milligram of the stuff per liter. That is tiny, right? It's 0.001 grams in a full liter. And 1 parts per billion is literally 1 part of the thing per billion parts of water. And it's by mass. It's always by mass. So it's 1 microgram per liter of water, or whatever you might have. You might hear, actually recently we broke the CO2 record. It's 417, I think, ppm right now. So parts per million. So for every million molecules of air, 417 of them are carbon dioxide right now. So that's a ppm for a gas solution. So those are tiny concentrations, but we have to get into molarity. This is the good stuff. This is what chemists like. So I'm going to set that up. I'll pause, and I'll be right back. All right, so this is the one that the chemists like. We like to express things in moles per liter, or sometimes, millimoles per milliliter, or any kind of thing like that. Moles per liter are the ones that we like. It's called molarity, for obvious reasons. It's molarity. The symbol is M, big M, and big M stands for moles per liter. So when you see big M, it's always moles per liter of the solution. And as already discussed, it's per liter of the solution. It doesn't mean that there's 3 moles in the container, because I could use half the container and it keeps the same concentration. That's some symbol, moles per liter. For example, 1 mole of sodium chloride, which has a molar mass of 58.44 grams per mole, in a liter of water, it's 1 mole per liter. If I then, use half of it, and I've got 500 mils, I've still got the same concentration of salt. It's still 1 mole per liter. I've just got fewer liters. So I've got half a mole in half a liter, which is still 1 mole per liter. Right? So it doesn't change with volume. It means we can just stick it on the shelf, and we know that we have that many moles of it per liter of the solution all the time. Kind of like, no matter how much of this vinegar I use, it's always 7%. It's always, my 1 mole per liter solution is always going to be 1 mole per liter. We say molar a lot, 1 molar, 2 molar, stuff like that. Calculate it, very simple. It's moles per liter. You literally divide the number of moles by the liters of the solution. That's it, moles per liter. Here's a formula, C equals N over V. Usually we measure in milliliters, so you kind of have to convert to liters first. So 200 mils is 0.2 liters. 500 mils, 0.5 liters. 25 mils, 0.025 liters. Divide by 1,000. But question is why? Why is molarity so good? Well, the thing is, it's the solutions, they have the same number of compounds per liter, and number is what we care about for reactions. Right? Number is what we care about for chemical reactions. Moles is what we care about for chemical reactions. So when I mix 2 aqueous solutions, like for example, hydrogen chloride, hydrochloric acid, and sodium hydroxide, an acid and a base, and I want to neutralize them, it's a 1-to-1 ratio in the reaction. 1 sodium hydroxide to 1 hydrochloric acid. If I have 1 molar, 1 mole per liter, and 1 molar, 1 mole per liter, I can mix them, and as long as I have equal volumes, I know that I'll have exactly the same, right? I know, 25 mils of one and 25 mils of the other, because they have the same concentration, and it's a 1-to-1 ratio in the reaction. It's great. Even if they're different, right? If I have 2 moles per liter HCl, 2 moles per liter, and 0.5 moles per liter sodium hydroxide, then the HCl is 4 times more concentrated. I have 4 times more atoms of it, more molecules of it per liter than I have of the sodium hydroxide. So I need to add 4 times more of this compared to one of these, and I don't have to do a lot of calculation with it. It's great. Moles per liter are super useful, and calculations with concentrations are very nice. This is harder with other measures. If this was in grams per liter or something, or in percents, then I'd have to do some calculations. I'd have to pull out a periodic table and do some work. But no, this gives me moles directly. As long as I know how many milliliters or liters, or how much volume I have, I can get moles right out of it. I don't have to worry about what the chemical actually is, which is pretty great. That's why chemists like it so much. We're going to finish off with some practice problems. So, here's a formula of it, and here's a sample problem. I'm going to start with this sample problem here. Coca-Cola has 39 grams of sucrose per 355 mils of beverage, so of Coca-Cola. We have to determine the concentration, the sugar concentration, the sucrose, in moles per liter. So I have grams, which is my solute. That's going to need to be in moles. I have my milliliters, which needs to be in liters. So that's what I'm going to set up over on the whiteboard. So I'm going to pause and get that set up on the whiteboard because it's getting to be a pretty long video so far. Okay, so I've got my my stuff set up over here. I've got 39 grams of sucrose per 355 milliliters of Coca-Cola. I wrote down the grams per mole, the molar mass of my sucrose. I decided to spare you guys the trouble of doing 12 carbons and 22 hydrogens and 11 oxygens. I need to convert this into moles per liter. So I'm going to take my 39 grams and convert it to moles. I'm going to take my 355 milliliters and convert it to liters, right? That's what I need to do. So let's convert this to moles. 39 grams of C12H22O11 times, I'm going to do my conversion factor here. Here's my conversion factor, grams per mole. I need my grams on the bottom and my moles on the top. So for every 1 mole, I have 342.3 grams. So I'm not going to have a lot, and you can run it through the same thing, right? Same mental thing. Do I have more or less than a mole of it? And clearly it's going to be less than a mole, because 1 mole is 300 milliliters, 300 grams, 342 grams. So 39 divided by 342.3, 0.114. 0.114 moles of C12H22O11. Now, 355 milliliters is how many liters, right? How many liters? Well, we can do a conversion factor if we want, right? 1 liter is 1,000 milliliters. My milliliters is going to cancel out, so I know I divide by 1,000. So that's 0.355 liters. 0.355 liters. So if I divide that, right, I divide them by each other. 0.114 divide by 0.355. That's equal to 0.114 divided by 3.5 in moles per liter. So I'm just going to write it out just so you see the moles per liter come out. 0.355 liters, which is equal to 0.32 molar C12H22O11. Yeah, so that's our answer, 0.32 molar. That's what you convert. This is really a good kind of scheme here. The grams needs to be moles, and the milliliters needs to be liters. So that's our first practice problem. We'll go to our next practice problem. Just give me a sec to set that up. All right, here's the second sample problem. It's asking what is the molarity, molarity is moles per liter, of a 3% weight by volume H2O2 solution. So I'm going to set that up over on the whiteboard. There we go, we're on. So we have 3% by volume, 3% weight by volume H2O2, right? H2O2. Just a second, I'm going to pause. the question is, what does it mean? What does 3% weight by volume mean? Well, as we talked about earlier, weight by volume is grams per 100 mils, basically. Grams per 100 mils. Because, its weight is grams, and volume is, a milliliter of water is a gram of water, so that's what we're going with. So this tells us then that we have 3 grams of H2O2 per 100 milliliters of solution. So we have to convert that to moles and that to liters. Right. Kind of 2 ways to do this. I'll show you both, I guess, even though we're kind of running late on our time. So let's start with the molar mass of H2O2. H2O2, each oxygen is 16, so that's 32. Each hydrogen 1.01, so that's 2.02. So it's 34.02 grams per mole. 34.02 grams per mole. So 3 grams, we're just going to straight divide because that's what we did last time. 34.02 grams per mole is equal to, whatever, 3 divided by 34.02, 0.088 moles of H2O2, and 100 milliliters divided by 1,000 milliliters per liter is 0.1 liters. Right, so if we divide that, we're going to end up with 0.88 moles per liter. 0.88 moles of H2O2 per liter. H2O2 per liter. Or we just write M, right? Big M. Big M, H2O2. H2O2 per liter. Now the other option is, if you're a little bit clever, you can go, well, if it's 3 grams per 100 mils, right, it would be 30 grams per liter. Because 100 mils is 1/10 of a liter, 30 grams per liter. And then you just work out how much 30 grams of H2O2 is, and you get 0.88 moles. And you get the same answer. So that's our second practice problem. That's that. That's the end. To review, we talked about solutions, we talked about solubility trends with the weird gas drops in solubility with temperature, but solid increases in solubility with temperature typically. We talked about different measurements of concentration with percentages and things like that. And then we finished off with some sample problems for molar concentrations, which is what we're going to be working with pretty much exclusively. Tomorrow we're doing some stoichiometry with solutions. That's it. It's been a long video, but it's an intro. So yeah, thanks a lot, and I'll see you in class.